Patches of gas rise above the sun's surface.
The observations tell us that prominences are very cold and very dense structures compared to the atmosphere that surrounds them, which tends to be rather hot and rather low density. And this raises the puzzling question and the technical challenge of how to form these prominences and keep them suspended above the surface. We believe that magnetic fields create that support.
Telescopes can't see those magnetic fields, so scientists have to simulate them. The Navy team starts by stretching loops of magnetic field.
What we find is that as magnetic field underneath the loop is stretched out lengthwise quite a distance from the loop center, we find that the center portions of our stretched field lines dip. This forms the magnetic hammock, which is capable of supporting the prominence plasma against gravity.
Further stretching the field lines causes them to snap apart and connect to other field lines. The Navy researchers believe a frenzy of this reconnection triggers the prominence to erupt as a CME.
Think of the low-lying fields as, let's say, a helium balloon. They want to expand outwards. They're naturally very buoyant. They want to expand outwards, but overlying them are other magnetic fields. There are older magnetic fields that have been in the sun's atmosphere for some time, and those magnetic fields, they act like bungee cords holding down this helium balloon. The trick now is to remove these overlying fields very rapidly, have some mechanism to let the underlying field escape.
Attempts to simulate that escape mechanism crashed the supercomputer, which couldn't focus on the whole sun and the small region where field lines are breaking at the same time. NASA offered a solution in Paramesh. This software targets a simulation's mesh or grid where things are changing.
The best analogy is to soldiers on a battlefield. The general could distribute them uniformly across the battlefront, but that's not a terribly smart strategy. Instead, he focuses soldiers into groups where their efforts are most needed. Paramesh does that with the basic grid that modelers use to simulate events like this. It focuses the grid points where they're most needed.
Earlier, Paramesh helped show how matter condenses to form a prominence. For CME simulations, the magnetic field lines are where they belong, but do not yet reconnect so mass can escape. As the collaborators close in on the CME trigger, they envision predicting ejections before they happen. That would be a big advance on today's techniques. Currently, scientists watch the sun for CMEs heading our way. A few days before arrival, computers calculate where the storms will hit. Forecasting damage is trickier. The satellite trained to catch high-energy particles gives but 1 hour's warning. Companies and space agencies need to protect their assets. Later this decade, a fleet of new satellites will capture changes in the sun almost as soon as they happen. The data will feed into the Navy's simulations.
So the two things we're hoping to get from our calculations, from Paramesh, are one, several hours warning before eruption, but also a very accurate characterization of the CME as it propagates through the Earth, and therefore a very accurate prediction as to how geoeffective the CME will be when it hits the Earth.